Hello team, today we're going to look at AC power factor. That's right in front of us. This is final unit for module number 5, electricity systems. It is a reasonably complex mathematical one. In fact, I would suggest this might be the most difficult mathematics that we have to do on the course. Good news about that, of course, is that once we're through it, then that's the hardest maths done, and we can all breathe a sigh of relief. So I'm going to do this unit in 3 parts. I'll do a video here now on, I'll go through about the first half of the slideshow, then I'll do a video of the second half, then I'll do a separate video with maths examples similar to what you'll see in the test. So you get a chance to have a look at those, and then I'll dish out some practical examples for you to do on the maths. So similar to the last unit that we did, inductance and capacitance and AC circuits. Same sort of idea there. So again, I need you to work through all parts of this in order. I'm doing it like that for a specific reason. So you get first an introduction to the technical aspects here with the slideshow, and then there's some examples in the slideshow that I'll just talk through, and then some written examples that I've done where I can go through in detail with you, for you, on what I've done and how I've done it. As I said, those examples will be similar to what you'll see in the test, and then some examples for you to do. That's going to build your ability to ensure that you're going to be able to pass that test. Again, if you skip any of those steps and you go straight into the test, you are going to find that very, very difficult. If you are unable to do those practical examples without asking for anybody else's help, and going through it and doing them yourself, then you've got to ask yourself, I don't see any way that you're then going to be able to complete the test. But that's on you. That's for you to decide how you're going to do this. My suggested method. So let's go straight into this presentation then. So AC power factor. We've got a neat little picture here, which I quite like, the mug of beer, which kind of is an analogy for the relationship between those 3 power components that we kind of briefly touched on in the last unit. We have real power, reactive power, and apparent power. So our real power, remember, is the power that we can use. That's our resistive power. That's the power that's dissipated by the resistive components of our circuit. Reactive power exists. We're drawing that power from the supply, but it doesn't do anything. That's the power via the capacitor and inductor components, reactive power there. And then our apparent power is the total of both, and that's what we pay for. So the power that's being drawn from the supply is our real power plus our reactive power. You could also think of reactive power as imaginary power. It's there, it's measurable, we pay for it, but it doesn't do anything. It's useless power, if you like. So somewhat like the head on the beer. It's there, you're paying for it. I've got a glass of beer. I only have this much beer, but they're going to charge me for the whole thing, right? They're going to tell me that's a glass of beer, but I get this other bit on the top that's not really beer. It's there, but it's not the beer that I paid for. So ideally, when we talk about power factor, what we want is a power factor that is as close to a full glass of beer with as little head on it as possible. Yeah, decent analogy. Okay, so power in AC circuits, true power. The power that is supplied to resistors is referred to as resistive power. This is the power that performs the actual work of creating heat, light, motion, etc. It is also known as true power. True power is the symbol P, and its unit is the watt. The rest of the circuit current, it is the result of the circuit current and the circuit resistance, and can be found from the following equations, depending on whether they're series or parallel circuits. These are the same slides as we had in the last slideshow, so I'll go through them pretty quickly. P equals I squared R, or P equals V squared over R. The reason why we would use those 2 different equations, it says here, depending on whether they're series or parallel, both of those equations are still valid whether you're in series or parallel. That's not the point. The point is that in a series circuit, I could measure the current, and I know that the current is the same in every point on that circuit. There's only one current in a series circuit. So if I had the current, then I can do this calculation very easy, I squared R. And remember, I squared R is the same as V times I, voltage times current. Because if I took I out of this, if I wanted to find voltage, voltage would be I times R. I times R is voltage, and then voltage times current is power. So voltage, if IR is voltage, and IR times I then would be power, because that's V times I, then I could simplify that equation because I have I times R times I, or I squared R. So I would do this in a series circuit. I won't necessarily know the voltages. I don't need to know the voltages that are present on every component in the circuit. Just find the current, total current, and then use that resistance, I squared R, and away I go. Similarly over here, power equals V squared over R. We would use this usually more often in a parallel circuit, because again, in a parallel circuit, the supply voltage is the voltage that is present on every component in that parallel circuit. So if I know that voltage, then I only need to know the resistance, and I go V squared over R. Why is it V squared over R? The same thing as the previous question, same thing as the previous calculation. V times I is power. Power is V volts times amps. In this situation here, I don't have amps, but amps would be voltage divided by resistance. Voltage, if voltage divided by resistance is current, and then current times voltage is power, that means V over R would be my current times V to get power. V divided by R times V, or V squared R, V times V over R. So it's the same thing. Now, as I said, if I'm working with a series circuit and I know what the voltage is across one of the resistors, then I can just go V squared R in a series circuit, or I can do I squared R in a parallel circuit. There's no reason I can't. It's just usually, because we're in our series circuit, our current is fixed. In our parallel circuit, the voltage is fixed. Usually I would use V squared over R in parallel, I squared R in series. Reactive power, I won't read that, you can read that yourself. As I said, we've covered this yesterday, or well, I covered it yesterday. Whenever you're reading and watching this, might be a different day, but in the previous unit. So this is our reactive power, and again, we use Q for reactive power. X is our reactance, remember, because we have XL as our inductive reactance, XC is our capacitive reactance, so together we call it X. So this is the same thing. Q is our reactive power, so that substitutes for P in the previous equation. X is our reactance, which substitutes for R in the previous slide. So this is the same thing. Q equals I squared X, or Q equals V squared over X. We use Q when we're talking about reactance, the power that's dissipated in our reactive components, inductors and capacitors. We use X to talk about the resistance of those things. It's reactance. It's the same thing as resistance. It's just, this is the resistance in our capacitors and inductors. And we also we measure our reactance, our reactive power in volt amps reactive. There it is there, volt amps reactive, VAR, reactive power, Q. So it would be, if I was working this out, I'd go 425 VAR, something like that. And then we have apparent power. So apparent power we call S, and we work that out using impedance, or Z. Remember, our impedance is a combination of resistance and reactance in a circuit. So S then is our, Z is our total impedance, and that means that S then must be total power. That's the total power. So we would work it out using the supply voltage and supply current, total voltage, total current, and total impedance. So this is the power that I pay for. This is a combination of the reactive power that does nothing and the resistive power that actually does something that I do use. So this is the total. So this is what would be getting measured at the meter coming into my house, would be the S, and that's what I pay for, regardless of whether I get anything out of it. If it was all made up of reactive components, then I pay for it and I get nothing. There's no usable power. Okay, we've seen this before. This is a power triangle. just like with impedance triangles or any of these other things we've looked at, hopefully this is starting to look familiar now. Our true power, that's the resistive part. So resistance goes on the horizontal side. The reactive power is on the vertical side, and remember that reactive power would be then a combination of the inductive power on the inductor, power on the capacitor. I would add them together. One is up, one is down. I'd add them together, and then whatever the result is, that forms my vertical side. And then my true power is going to, my apparent power is going to be the hypotenuse between those lines. The hypotenuse between the two sides made up of true power and reactive power. And we'll use exactly the same formulas as before. It's all the same trigonometry. That's my phase angle there. If I drew this triangle for a circuit, and I put resistance in here, and I put reactance in here, and then this line would be my total impedance, and the triangle for power in the same circuit will look exactly the same, because all of the ratios are going to be identical. Okay. Sorry team, I took a short pause there because somebody called me on the phone, so I've paused the video and started again. For you it'll look like it's carried straight on. For me, that was about an hour ago, so I'll just try and pick up where I left off. My apologies if I repeat myself. So I think we went through this triangle, and I've talked about the relationship between power triangle and impedance triangle. Essentially they're exactly the same thing for a given circuit. Okay, so we could also derive our power triangle from the voltage or current phases associated with the circuit, and it's essentially the same thing as what I've just said. So here we have that reactive voltage is 30 volts, resistive voltage, so this is the voltage across the resistor, 40 volts, and then we've used those phases to come up with a resultant, which would be our supply voltage, right? Or we could just measure our input voltage, it would be the same thing. And then we see there that we've got 5 amps. 5 amps is flowing in a series circuit. 50 volts for the 50 volts total, 30 volts reactive, 40 volts across the resistive component. So then volts times amps is my power, right? So 5 times 30 would be 150 VAR, that's my Q. My true power here, 40 volts times 5 amps in that circuit would be 200, and there I have that there. And then obviously supply voltage is 50 volts, that's there. That would be the same as this hypotenuse here. And it's, as I said, exactly what I was talking about, that the triangle looks the same. It's the same thing. Here we have all the voltages, here we have power, but the triangle ratios will be exactly the same. You'll find that the phase angles will be exactly the same. So if we compare that power triangle to an impedance triangle, we can see there's a direct relationship between power and impedance. It can also be seen with triangles of the opposing effects. So it can also be seen with the triangles, the opposing effects of capacitors and inductors. So we have an impedance triangle here, we have resistance, or we have 2 impedance triangles here. We have resistance along the bottom. That's our impedance, is the hypotenuse, and this is our inductive reactance. See, it's XL, so it's the inductive reactance. And down here I have another triangle with XC, remembering that the capacitive reactance is in direct opposition to the inductive reactance. So the R would be the same. This triangle represents the resistance and capacitance in my circuit. This triangle represents the resistance and inductive reactance in my circuit. If I subtract the capacitive reactance from the inductive reactance, because they're both on the vertical axis, then I get one triangle which will have this side here be, as it says there, XL minus XC. The R side does not change, and then obviously the Z, the impedance, will change. My phase angle now gets smaller. So actually this is a little hint on power factor correction, right? Because if you think about it, if I added more capacitance, then the XL minus XC gets smaller and smaller. So as this gets smaller and smaller and smaller, then so my impedance, total impedance, will become closer and closer to my total resistance, and my angle gets smaller, which would mean, as we've just said, if the relationship between impedance and resistance is the same as between apparent power and true power, then the closer my apparent power and my true power are, and the smaller my angle, then the better efficiency I've got, right? My power factor is better. So power factor correction, right? In an ideal circuit, all the current in the circuit and the supply voltage will be utilized and turned into true power. So that's our resistive power. That's the power that's doing, remember, that's the power that's doing the work. True power is the power that's doing the work. However, in reality, this does not occur because of reactive components in the circuit. We have inductors, we have capacitors. So the circuit will exhibit some inefficiency. This inefficiency is a ratio of true power and apparent power and is known as power factor. It can be found by W over VA, where W is true power, so it's W because it's watts, and VA is apparent power, it's volts times, and it's total volts times total amps. So it's just a ratio, W divided by VA, or true power divided by apparent power. That's power factor, and it's just it'll be a number between 1 and 0. Remember, 1 would be perfect power factor, because if my W and my VA were equal, that means that all of my apparent power is being used. Then it'll be the W over VA will equal 1. It'll be perfect power factor, unity. It can't be more than 1. I can't have a true power that's greater than my apparent power. If this number was very, very low, so if my wattage was low compared to my volt amps, so my true power compared to my apparent power is very low, then I'm going to get a relatively poor power factor, and that means I'm paying for a lot of power that I'm not using. Power factor can also be found by using cos of the angle that is present between the supply voltage and supply current. So that's my phase angle, right? So that would be that angle there. If we think about it, cos of the angle. If we think SOHCAHTOA, cos adjacent over hypotenuse. What's my adjacent? That's that one, resistance. Hypotenuse would be this one here, right? Hypotenuse is the apparent power. Adjacent is true power. So adjacent over hypotenuse is the same as this, true power over apparent power. So by going cos of the angle, it's just giving me the same formula. It's true power over apparent power, because that's my A over H in the car of SOHCAHTOA, cos adjacent over hypotenuse. If that doesn't make sense, don't worry about it. Just remember to use this formula, or you can use the cos of the angle. A high power factor means that the electrical power is being utilized effectively, so high power factor being close to 1. While a low power factor indicates poor utilization of electrical power. Power factor can be expressed as either a percentage or as a ratio. If the load was purely resistive, it would be said to have a power factor of 1, or unity, because my apparent power and my reactive power will be the same. I have no phase angle, just apparent power and true power will be the same, so my power factor will be 1. However, most power factors are expressed as leading or lagging. This is because, as stated previously, current may either lead or lag the supply voltage depending on whether the load is inductive or capacitive. A leading power factor indicates a very capacitive load, where a lagging power factor indicates a very inductive load. In most cases, you'll have lagging power factors in inductive loads, because inductive loads are things like motors and transformers and ballasts, whereas capacitive load doesn't really exist. There's not many circuits that you'll have lots of capacitors and nothing else. So normally power factor correction is about connecting a capacitor onto an inductive load. So the effects of low power factor is low active power for apparent power put in. So that means I'm not utilizing all the power that I'm paying for. Increased supply current for a given active power. So to get a certain amount of power, if I need 2 kilowatts to power my thing, then I've got a low power factor, then I'm going to have a high apparent power compared to my true power, and my supply current therefore will be much greater than it should be for the power that I actually need. Increased capacity of supply equipment required, because if I have that additional supply current, if I've got to suck in 10 amps to power my 2 amp thing because of my bad power factor, then all of my all of my supply equipment, all my cables and switches and stuff have to be rated for that higher amount of current. And higher power bills because to get my 2 kilowatts of useful power, I have to pay for 10 kilowatts because my power factor is so bad. So the benefits of power factor correction then: reduce electricity bills, increase system capacity. So if I have a system that can operate at 10 amps, or let's say 100 amps, and I give myself a better power factor, then I can still use that 100 amp capacity of my system, but I can use more of it. So I can add more things into my system, greater capacity. More efficient use of power supplied, more stable voltages. We saw, I think, in the last topic that voltages could get very, very high if we have lots of inductive or capacitive loads. Reduction of harmonic waves and wave distortion. Greater power can be drawn from the supply. You don't give unused power back to the power supply company. It's the same as reduced electricity bills and less heat generated. Ideal power factor versus realistic power factor. An ideal situation would be for apparent power to be equal to true power. Therefore, the power in the circuit will be fully utilized and not wasted. The circuit will have a power factor of 1 or 100%. So it's a purely resistive circuit. In reality, most industrial situations consist of electric motors and lighting systems that are highly inductive and have lagging power factors. As I said before, it's more common for us to see lagging power factors. To make the circuit appear purely resistive, there must be little or no reactance. So to get no reactance in the circuit, the inductive reactance that's inherently part of the circuit, as it says there, motor or lighting inductive loads, we would need to add in capacitive reactance to cancel that out. So by placing a capacitor across an inductive load, we can increase the overall power factor of the circuit from the supply point of view. Should note, however, that the power factor of just the inductive part of the circuit remains unchanged. So if I have a capacitor there, then I've still got wires between my inductor and my capacitor. So the power factor of that part of it after the capacitor would be the same. The capacitor would change it from the input. The capacitor in the circuit causes a leading current to be taken from supply. This in turn cancels out the lagging current being drawn from the inductive component. Thus, the overall power factor becomes better and less supply current is required. This can be seen by comparing the following phasor diagrams. Here we go. So here is my my current here for my resistive current, and here is my lagging inductive current. And you can see that the resultant of that is this bad power factor, large current. We can see that line there, that's my supply current, is a lot bigger than the current that I'm actually utilizing here on the resistor. So if I add in some capacitance, what that does is it changes. You can see there's the three sides of my triangle. I take the capacitive current away from the inductive current so that the vertical side of my triangle is smaller, and then you can see that angle is now less, and this line, that's the supply current, is now shorter than it was before. All I've done is added a capacitor, and it's actually changed how much current my circuit will be drawing. It is possible to improve the power factor of a circuit to unity. Of course, it's possible. If I have the exact same capacitive reactance as I have inductive reactance, then my power factor will be 1. However, this is not done in practice due to the following reasons. Firstly, a situation of resonance may occur in the circuit, leading to possible dangerous levels of current and voltage. If you look at the example on the previous module or previous video, you'll see that as that power factor approaches unity, the voltage on the capacitor and the inductor gets really, really high, much higher than the supply voltage. So that's an issue. Secondly, to increase the power factor by as little as 5%, a large amount of capacitance is required. It's leading to high costs. So although it will save us some money from in terms of the power that we pay for, it will cost us some money. We have to go and physically install a lot of big capacitors. Alright, calculations for power factor correction. As seen, the Power triangle to the right is a right. Let me start again. As seen, the power triangle is a right angle triangle. All power triangles are a right angle triangle. With the use of trigonometry, power in an AC circuit or installation can be found by knowing just a few elements that make up a circuit. True power is equal to apparent power multiplied by the cosine of the angle. Why? Because that's trigonometry. It's SOHCAHTOA again. So cos true power is equal to apparent power multiplied by the cosine of the angle. So that's my adjacent. That's my hypotenuse. So we're saying cosine of the angle, cos of the angle times the hypotenuse equals the adjacent. SOHCAHTOA. Reactive power is equal to the apparent power multiplied by the sine of the angle, because that's reactive power is the O, and the apparent power is still my H, so SOH, SO, sine of the angle times the hypotenuse equals the opposite. SOHCAHTOA again. I could also, if I knew two of those numbers, if I use the angle to work out my true power, then I could just use Pythagoras to go 200, 250, and I can use that to work out the length of the third side and work out my reactive power. Or vice versa, if I knew reactive power and true power, I can work out the other one. Okay, I think I will stop there, and I will come back and do another video with these maths examples in it. As I said, I will just talk through these ones that are in the PowerPoint, then I will do a specific video where I work through some examples I've done myself, and then you can do some examples too. Okay, see you at the next one.